For our demo of conservative GC, we'll write it in a semi-portable way by including a definition, a macro definition that changes a main to original main, and then the garbage collector gets to provide its own main that will eventually call original main. But before it does that, it remembers the stack position right now. And it remembers the stack position right now as an approximation. If we assume that the argc variable, it's a local variable here, if we assume it's stored on the stack, then stack init gets us roughly the current position of the stack. And then when we actually perform a GC later and we're looking for all the roots, then if we take a local variable stack now and set it to its own address, if stack now is stored on the stack, now we have two addresses that bound all of the other variables that are on the stack. There's absolutely no guarantee that this will work in C, but C as compiled by GCC on Linux, x86, 64, and so on, if you have all of these assumptions, then the garbage collector can generally make something that does actually work. And we'll see that in our example. Collect garbage then, it's going to work the same as before. Mark and sweep from roots is exactly the code that we had before. All we have to do is fill in the root table every time by inferring it from the stack. So that's what find roots does. And here's our implementation of find roots more completely. We get some approximation of the current stack pointer so that we can look at all the variables in between. And so we just are going to take this stack now. Since the stack grows up, we will keep incrementing it until we get to the original position of the stack. If a value on the stack at that position, we're just looking at raw pointers in memory, if it looks like an allocated pointer, then we'll assume that that current address in stack now, that is a local variable root. So every time we perform a GC, we're going to fill in the root addresses that way. How do we know if this pointer is to an allocated object? Well, it's in the range of one of our chunks, and for our purposes here, it has to be properly aligned also. So as long as it has those properties, then we'll assume it's a pointer to a node. If we put these pieces together, then it's in the CGC part here, and you can see there's collect garbage, which is find roots, and then the mark and sweep from roots that we just saw. And there's the other code. And if we run tree CGC, then it's running the same collector as our more precise collector. And in fact, we see it gets exactly the same peak memory use. That's because in our very simple benchmark program here, there's no pointers to confuse. There are no local variables that turn out to be dead, or they refer to objects that are in the tree anyway, and so we get the same kind of memory use that we got before. In more realistic, more complicated settings, this number is going to be higher than that number, sometimes by a lot, sometimes by just a little bit.